Okay, we're going to work on some calculus of polar curves. Specifically, we're going to look at some derivatives, um, and I think we're going to look at possibly arc length too. So we're going to look at some examples. These are the things I promised you guys. And we'll start off with the proverbial find the slope of the tangent line. So we're going to find the slope of the tangent line to the curve at the indicated, I'm not going to say point, I'm going to say, I could say parameter, but your book says at the indicated point specified by the value of theta. So, okay, we can say at the indicated point. We don't even have the address though. Specified by the angle theta here. So we're going to go into some of those details. And so the first example that we'll look at is going to be, we're going to look at the function r is the natural log of theta. And the angle they're going to say is E here. Okay, so here's r versus theta, and theta is the angle E. I want you to note something here, that theta needs to be strictly positive because the natural log, ladies and gentlemen, is not defined at 0. But it is defined at 2 pi. So we can find what that is at the pole. However, I just want to say you can't use an angle theta being 0, a 0 angle, but we can use theta as 2 pi and so on. Just positive values for theta. And what I did earlier was, in Desmos, I got a sketch of this curve. So this is a curve here, r is natural log of theta, and I just put this from 0 to 2 pi, although, like I remarked, theta can't be 0. So, but theta could be 2 pi, it could be 4 pi, and so on. So I could even change this here and say, for example, 4 pi, and you can see the additional information that we may get. And 4 pi is about 12, so you guys know. So here's a very, very fascinating polar curve. We just want the slope of the tangent line at the value E, which is about, the angle theta being E, which is about a radian measure 2.78. So 2.78 is very, it's a small value. Well, theta is E 2.78. If theta is pi, that's 3.14. So it's going to be somewhere in quadrant 2, right? So I just want to make a remark here that in quadrant 2, we're going to find the slope of the line tangent to the curve at this point. Anyway, let's take a look at that. And so if you go back to your notes, we need to find how to get a derivative. And this is the work we had. Since I'm here, I'm going to try to clean a little bit of this up. I apologize. Okay, so it's clean. So we need to find out, here's our formula here. dy dx is found by, in short, r prime sine theta plus r cosine theta, r prime cosine theta minus r sine theta. So we need to write that down. Okay, so dy dx, if you go back, r prime sine theta plus r cosine theta. And then we have r prime cosine theta down here minus r sine theta. So let's double check and make sure. Okay, r prime cosine theta minus r sine theta. And remember the numerator here, dy d theta, is what you see up here. And the denominator, dx d theta, is what you see down here. And now, as you guys can see, what we need is an r prime. Okay, we already have r, but we need r prime. Now, r prime is going to be, by definition, right? R prime is dr d theta, and r here is the natural log of theta, which is 1 over theta now. So here's our r prime. So we're going to replace r prime here with 1 over theta. And r, we know, is natural log theta. So we replace r here with natural log theta. So this derivative here is dy dx. Let's put sine theta over theta plus natural log of theta cosine theta divided by cosine theta over theta minus natural log theta sine theta. And let's be consistent here with how we write this. Okay, let's use our parentheses, theta. Okay, this is the derivative. This is dy dx. But they want to find the slope of the tangent line. Okay, now this here, if you guys remember, this is the slope. That's m tangent, because they want the slope of the tangent line. M tangent, if you guys recall, in this case here, right, is dr d theta evaluated where theta is e. So this here is the definition of that m tangent. So we're going to have to really plug in now here theta being e. And if we want, let's draw a straight line, right? Okay, so now just plug in e wherever you have a theta. And you end up with dy dx sine e over e, the natural log of e, cosine e over e, minus natural log e, sine e. Now remember, the natural log of e is 1, so this is gone. And I'm going to say something here. Let's see, we can simplify this. I'm going to do something like this. I'm going to say to you, multiply the top by e and the bottom by e in each case, right? Oops, sorry. And you might say, well, what does that do for us? Well, here's what it'll do. We'll have sine e over e minus e cosine of e over e over cosine e minus e, oh, sine e, yeah, sorry about that. E sine e over e. And just doing a little bit of algebra here, and you'll end up with sine e minus e cosine of e, everything over e here, and you get cosine of e minus e sine e. Over that e, we get a complex fraction, and you're going to end up with, when you do the division of a complex fraction, doing that algebra, you get sine E minus E cosine E minus E sine E, and I think there was a plus in the numerator. Yeah, so here's my numerator. It's still there. It's still there, and it is still here. This is again my M tangent. Slope of the line, tangent to the curve, at the indicated point, and they didn't give you a point, they just gave you at the angle. At the angle, don't forget, at the location where theta is the value E, and that's a radian measure. E is about 2.718, so that's less than 180 degrees. It's a quadrant 2 angle, so you guys know. Okay, because of the value of E. So here's an example of simply using or trying to, use the derivative, find dy dx. Okay, now we're gonna do another one here, and we're gonna do r is sine 3 theta. So we got r is sine 3 theta, and the angle in this case is going to be pi over 6. So theta here will be pi over 6. Now remember, you need dr d theta, because this is what our r prime is. And that's the derivative with respect to theta, sine 3 theta, which is the derivative of sine is cosine 3 theta, but don't forget to take the derivative by chain rule. All right, by chain rule of 3 theta. And the derivative of 3 theta is actually going to be 3. So r prime becomes 3 cosine 3 theta. Now, this is what we're going to use. And it's the same question as the last one. They want dy dx, which is r prime. Now go back over here. Remember our formula. Sine theta plus r cosine theta. R prime sine theta plus r cosine theta over r prime cosine theta minus r sine theta. You already have your r prime, and that's where we replace it here. It is 3 cosine 3 theta. In this case, r is actually up here. Sine 3 theta. So we replace that with a sine 3 theta. Here's what you get all together. Dy dx is 3 cosine 3 theta sine theta plus sine 3 theta cosine theta over 3 cosine 3 theta times a cosine of theta minus sine 3 theta times sine theta. And if you like, let's make this line nice and straight somehow. There we go. And this is our derivative. This is dy dx. So just double checking a few things. Yeah, double checking my notes. 3 cosine 3 theta sine theta. Yeah. Plus sine 3 theta cosine theta. 3 cosine 3 theta cosine theta minus sine 3 theta sine theta. Okay, now let's remember what theta is. Because again, they want the slope of the line tangent to the curve at an indicated point represented or specified by this angle theta here. Same question, we need M tangent. So M tangent, we have to plug in theta is pi over 6, right? Did they say? Yeah, theta is pi over 6. Let me double check. All right, yeah, and pi over 6, so you guys remember, you get an idea, that's about 30 degrees, right? It's not approximately, it's exactly 30 degrees. So you might say to me, okay, Mr. Judge, why is that important? Because when you go back and you actually, let's try a different color here. If you guys remember, you're going to draw a equilateral triangle here. Okay, so this is 2, this is, well, this is supposed to be 2, this whole distance, and this is 2. From this equilateral triangle, we're going to get our right triangle. $30 degrees up here. This is 60 degrees. 90. This becomes 2, 1, and by Pythagorean theorem, that's a square root of 3. So we need sine and cosine of this 30-degree angle right up here. This is 30 degrees. So what that means is sine of pi over 6, which is 30 degrees, use the definition of what sine is. Sine is opposite over hypotenuse, which is 1/2. Similarly, cosine of pi over 6, this is adjacent, so it's a square root of 3 over 2. So sine pi over 6 is 1/2, cosine pi over 6 is a square root of 3 over 2. So we already know for some of these answers, because we're going to have to plug in for theta, you're going to have to plug in here pi over 6. We're going to get that one. Pi over 6. Pi over 6. Pi over 6. But then you also have here 3 pi over 6. And you say, what is 3 pi over 6? 3 pi over 6 becomes pi over 2. So I'm not saying this is theta. It's 3 theta. 3 theta. 3 theta. 3 theta. So let's remark. 3 theta is really 3 times pi over 6, which gave you that pi over 2. And we plug that in as well. Now this is nice because pi over 2 is 90 degrees. And whenever I think of, for example, sine of maybe, what's sine of 90 degrees? Well, sine of 90 degrees is 1. So this value is 1. Wherever there's a sine of 90, and here's where there's a 90, that's 1. But we also have cosine of 90. Now, that's nice too, because cosine of 90 is actually 0. Because pi over 2 is 90. So let's think about that. Cosine curve, yeah, that's 0. So what really is happening here, what we have, since we just have this portion here, since this other portion has, 3 times 0, that's gone. And I don't care what sine pi over 6 is. 3 times 0 down here again. I don't care what cosine pi over 6 is. That's gone. That's 0. Anyway. All right, let's see. dy dx becomes, here's what we're going to have. Let's go back and think. What was cosine pi over 6? You said cosine pi over 6. Because I have it right over here. Cosine pi over 6. Well, that's the square root of 3 over 2. So let's put that there. And then similarly, sine of pi over 6 is 1/2. So we got to find that one. Here's sine of pi over 6 is down here. So it looks like we have on the numerator 1 times the square root of 3 over 2, and in the denominator that's minus 1/2. So let's put that together here. That was 1 times the square root of 3 over 2, and then minus 1 times 1/2, which is going to be minus square root of 3 over 2 over 1/2 another complex fraction, which is minus square root of 2. So my derivative is minus square root of 2. And let me go back and be specific. That's not the derivative. That is our m tangent, right? You guys remember, that's m tangent. So let's write it down correctly. That's the slope of the line tangent to the curve at the indicated point, represented by the angle theta is pi over 6. Now, go back to the language. The language is asking here, specifically, at a point, indicated point. A point that they're talking about, you got two types. But this is rectangular, right? We have polar, which is r theta. And if you said, well, where is the location in polar form? Well, in polar form, if you go back to the curve, here's the angle theta. You have to plug that in here. You get sine of pi over 2. And we already talked about r is really going to be sine pi over 2. Well, that's 1. So in terms of a polar location, r theta 1 comma pi over 6 for this curve. This is r sine 3 theta. That's the polar representation. And if I go back to our graph here, I already have it for us, so you guys know. It's right here in blue. Okay, remember pi over 6 is 30 degrees here. And I want to let you guys know, specifically, if you had to graph this curve. Let me try to do this, take the picture again. Right, so I can draw on this thing. 1, radius is 1, pi over 6, 30 degrees. That's actually, let me go here and change that color here. I would kind of like purple today, maybe. That's actually right here, so you guys know. This is 1 pi over 6. That's the polar location of this. We're going to have a tangent line at that particular location. And all we found was the slope, m tangent, was negative square root of 3. But when they say point, what they really mean is rectangular, meaning an x-coordinate and a y-coordinate. So even at this, I should say, since this is the r theta polar representation of the point, right, we have a rectangular representation of the point. So, I mean, they can actually ask you that very proverbial question, what's the equation of the line tangent to the curve at that location? What you would need to do is you'd have to use the point slope form, where y minus y1 is m times x minus x1, like you guys have been doing. And you'd simply have to convert this from polar to rectangular. You have x equals r cosine theta, x equals y equals r sine theta. So if I said, let's go back here, and we know r is 1, theta is pi over 6. We want to save that maybe. I don't know where we're going to save it. Save to, let's save to photos. I don't know. Saving it to files the other day, right? To just remark about this thing called a point, the equation of the line tangent to the curve, y minus y1, which is m times x minus x1, when they're saying point, very often they're referring to this rectangular coordinate. And then you'd have to actually convert. And I'm going to change that color again. This is x will be r cosine theta, and y will be r sine theta. And you already know 1 pi over 6. So the x-coordinate will be 1 times cosine pi over 6, and the y-coordinate is 1 sine pi over 6. So the x-coordinate is actually, we found cosine pi over 6 somewhere. Yeah, it's square root of 3 over 2. And y, we found that one, sine is 1/2. So we got the x-coordinate, we got the y-coordinate. So I got the square root of 3 over 2, comma, 1/2. This is the rectangular coordinates. So if you had to go back and really, do this kind of question here, you just go back and replace everything and say, okay, I found that m tangent was minus square root of 2 m tangent. And the y-coordinate was, just found it right now, 1/2. The x-coordinate was the square root of 3 over 2. So I'm going over these kind of details because, in the last test, some people kind of made some mistakes with this and say y minus 1/2 is minus square root of 3, x minus square root of 3 over 2. Let's double check. Yeah, and the rest is algebra. So my y minus 1/2 is minus square root of 3 x plus, looks like it'll be 3/2. Add 1/2 to both sides now. So the equation will be y equals minus square root of 3x. 3/2 plus 4, 1/2 is 4/2, which is really 2. So I wanted to remark about this. This again is what we call that L tangent. And what you found, this was M tangent. So this is not really the question they gave us originally, but once we get the slope, you can find, in many cases, not every case, but it could be, depending on the curve, depending on the point, it might be very nice to find the equation of line tangent to the curve, and this is the line. Notice it has a negative slope. And I wish I didn't, delete the curve, but as you guys can see, oh, I guess I'll try to do something here with this. Here's a device, since I'm talking about it. At that location, you're going to have a y intercept there, and yeah, you're going to have that negative slope here. So I just want to see that. Sticky. Yeah, you guys get the point. There's the location of M tangent. Okay, this is how we find that. Remember, this location, this is actually x is square root of 3 over 2, and y is 1/2. And that makes some sense here. So if you can draw a line, if I can't mess it up, maybe, oh, there we go. Can I rotate this at all? Please say I can. Is there any way to rotate this so I can draw a nice, oh, there is. Wow. Boy. That's amazing. Oh my God, look at that, ladies and gentlemen. L tangent, essentially. Beautiful. Wow. And yeah, notice that it's a negative slope. And it goes through that line at 2, or the point, the y-intercept at 2. So everything you guys learned and loved from beginning algebra, is right here. And this is putting this together, right? This is calculus of polar curves, specifically derivatives and some arc lengths. Yeah, I like that. Let's save that one. You know, I don't know. Save the photos. Who knows? Okay, now let's go on a little bit, and we're going to still look at some derivatives and see some things that are still interesting, like finding points on a curve where the tangent line is horizontal or vertical. So now they're going to say determine points where the tangent line, altangent, is horizontal or vertical. So we're going to try one that says x equals r cosine theta plus sine theta. Here's this curve. So we need to find points on this curve where the tangent line is horizontal or vertical. And I want to remark here, I did as well, take a look at this curve. And as you guys can see, this particular curve here, it's a circle. So r is cosine theta plus sine theta is actually a circle. I'm kind of tempted to prove that that's a circle to you guys, just because, you know, we can have a little fun with these today. Okay, it's a nice day. We can do a little, look at this. This is a circle that looks like it's centered at 1/2, and the radius might be more than 1/2. Yeah, interesting. 1/2, 1/2. So you guys see the center maybe? Let's take a picture so we can write on this. So right in here, and let's change the color to green since we're looking at a green picture. But I kind of want a nicer green than that. Okay. Looks like your circle has a center right in here. That address looks to me to be 1/2, 1/2. And let's learn how to write 1/2 if we can. And what I'm saying is that this radius of this circle is bigger than 1/2, and we're going to find what that is. And by the way, the essence of this question again was, where do you have horizontal and vertical tangents? Vertical tangents happen at these locations. So in red, if I get out my ruler again, and we can figure out a way to use that, there we go, 90-degree angle. There. Slightly more over. Here is our vertical tangents, right? Altangent, altangent. Remember what we need to know about the slope. Those slopes are undefined, right? Slopes are undefined. I'm going to change colors though, because this is the location. We have a circle here where we're going to have some horizontal tangents. I really think I like this ruler. Boy. And you got altangent here. We lost our color blue. We lost the pen. Altangent. We'll put it over here, altangent. And again, this is when the slope is equal to 0. So you have this undefined situation, right? This is undefined. The limit does not exist. Derivative, right? And anyway, I don't know where we got something like this. Let's clean this up. I like this picture too. Let's get rid of the ruler. There you go. So this is kind of what's going on. It looks like we have a circle. The radius is bigger than 1/2. If I go back and write that down, I want to. So my radius of that circle is bigger than 1/2. We're going to check that out. And we're going to find locations of vertical and horizontal tangents here. And we're going to do it in the polar form here. So let's go back to this. And I want to save this picture. My gosh. Okay. So we're saying that this is a circle. So you guys, here's kind of how you go about this here. We're going to have a little fun today with this. We know r is cosine theta plus sine theta. We're going to square both sides here. All right, you know what you can do? Yeah. Well, should we prove it's a circle right now? Well, not square. You don't want to square both sides. This is actually going to be complete. Okay, let's complete this. Let's do it. Whatever. Multiply both sides by r. Okay. This is what this is, so you guys can see this. R squared becomes r cosine theta plus r sine theta. By definition, x is going to be r cosine theta. R sine theta is y, if you guys remember. And then I'm going to say r squared. I don't mean to erase that. This is x squared plus y squared. So here's what you end up with. X squared plus y squared is x plus y. Now, we're going to subtract x and y from both sides. And here's what I started to say to you. That we're going to get now x squared minus x plus y squared minus y, and that will equal 0. And you say, that doesn't look like the equation of a circle yet. I'm going to say, complete the square. And you say, with what variable? Both x and y. So if we complete the square, you're going to go to that b value. They're both the same, right? So this is that b. So you start with you start with b over 2. If you guys remember the process for completing the square. That's negative 1/2. We're going to use that. Second step is you're going to take the negative 1/2. You're going to square it, and you get 1/4. You're going to use these values. And this is actually going to work for both the x variable and the y variable because you have the same b values. So here's how you can look at that. Remember, this is going to be x squared minus x. You always use the r squared value. So in other words, you add 1/4 and then you take it away. And then you do the same for the other one. Y squared minus y, the y coordinate, because it's the same values, plus 1/4 minus 1/4. You could do it this way. Some people do it this way, some people don't. And then I'll say to you, factor the first 3 terms for both. And then you might say to me, well, do I really have to factor this perfect square trinomial? I'll tell you, like I tell my other students when we cover this topic, you don't really have to factor. You're going to always use the values found in step 1, this minus 1/2. That always goes, ladies and gentlemen, down in here. And you do this for the other one. Oops, sorry. You do it for both since it's duplicated, right? Same values. I got that minus 1/4 plus y minus 1/2 squared minus that 1/4 equals 0. Now notice this, by some arithmetic here. You're going to add these two negative numbers. Negative 1/4 plus a negative 1/4 is negative 1/2. Okay, so altogether we have x minus 2 squared plus y minus 1/2 squared, I apologize, minus 1/2 is 0, but of course you add the 1/2 to both sides and you end up with x minus 1/2 squared plus y minus 1/2 squared, and that's going to be 1/2. Now, this is an equation of a circle. The center of the circle is at 1/2, 1/2, and don't forget, this is actually r squared. So r squared is 1/2, or r is plus or minus square root of 1/2. Well, it's a radius of a circle. We only take the positive value, and then that's square root of 1 over the square root of 2, and that's 1 over the square root of 2, ladies and gentlemen. But r here, if we rationalize, the denominator is a square root of 2 over 2, so that's about 0.07. You guys know if we approximate this is 1.4 divided by 2. R is approximately not 0.7, 0.7. So our radius, ladies and gentlemen, is going to be the square root of 2 over 2 for this circle. So as we said, I was right with the center. The center was perfectly fine. And I was right with the radius. It was bigger than 1/2. Interesting. Anyway, so this is converting a polar equation to a rectangular equation, and sure enough, we are looking at a circle centered at 1/2, 1/2, and the radius is slightly bigger than 1/2. It's 0.7. So pretty good stuff today. Nice. Now let's not forget what we're trying to do with this. Finding where this is what? Horizontal, vertical tangents. M tangent is 0. However, M tangent, if you guys remember, is not, I'll take up more space here. M tangent is actually okay. So we need to go back and remember, for horizontal tangents, this is what we're going to use here. dy d theta needs to be 0. This is for horizontal tangents. For vertical tangents, dx d theta is 0. Okay, so we're going to use that equation, and notice what this does here. If we go on top, this is where we have horizontal tangents. dy d theta will be 0, and this is what we're going to have to differentiate. So d theta is r sine theta. Don't forget, r was cosine theta plus sine theta. So I'm going to have to differentiate. You say r sine theta, and we set that equal to 0, but don't forget what r is. It's cosine theta plus sine theta. We have it right here. So this is going to give us, we need to do this product, and I'm going to do it on the iPad since I'm running out of space here. So r sine theta d theta r sine theta, right? Because this is my dy d theta. That's the numerator. That should be 0. I got to replace this r with cosine theta plus sine theta. And we end up with d theta cosine theta plus sine theta, and that's going to be multiplied everything with the sine theta. So I get d theta of cosine theta sine theta plus sine squared theta. Now, I can differentiate this in where I have product rule here, and that's plus sine squared theta. So here's what I think I'm going to do. I'm going to do a little something because, let's see if I remember, sine 2 theta, I believe, is 2 cosine theta sine theta. So that implies I can replace sine theta cosine theta with 1/2 sine 2 theta. Now, if you didn't want to do that, well then, you know, all you would have to do, I guess, is the product rule. Anyway, let's try this out. Let's see what we get here. Okay. d theta. Let's replace cosine theta sine theta with this 1/2 sine 2 theta plus sine squared theta. And by properties of derivatives, let's say 1/2 d theta sine 2 theta plus d theta sine squared theta. Derivative of sine is cosine, and don't forget by chain rule, derivative of 2 theta is 2. And derivative of sine squared, 2 sine theta cosine theta by chain rule as well. So that looks like I have cosine 2 theta here plus, and you say you got 2 sine theta. Don't forget, this is 2 sine theta cosine theta. Well, we replace 2 sine theta cosine theta with sine 2 theta here. That might help. Okay. Plus sine 2 theta, and that derivative is supposed to be 0, right? So we have, where is it? Yeah, dy d theta equal to cosine 2 theta plus sine 2 theta. Okay? Set that equal to 0. So if we do that, we end up with cosine 2 theta plus sine 2 theta equals 0. And that's going to give you a nice trig equation. You could do, well, subtract one term. You get cosine 2 theta is minus sine 2 theta. Divide both sides by cosine 2 theta. And essentially you're going to get tangent 2 theta is -1. You can actually do it this way. You keep that positive and the other one negative. Okay? Either way. And let me double check. Is that what we get? Tangent 2 theta is -1? Yeah. And we're going to have to be careful here with this. I'm going to remark about this equation here. Tangent 2 theta is being -1. What that really means here is that 2 theta, what are the angles? Where is tangent going to be -1? So we have to think about this here. Let's go back and think, right? Tangent alpha is -1 when alpha is going to be, remember that's in quadrant 1, 2, and 4. So it's 1, 2, it's alpha is going to be 3 pi over 4. And then opposite that, right, in quadrant 4, you have 1, 2, 3, 4, 5, 6, 7 pi over 4. And really, if you wanted the general solution, alpha is going to be 3 pi over 4 plus n pi where n is some integer. Okay, now that's not what we have here because of the fact that we're going to let alpha be, this is a change of variables. Alpha is going to be that 2 theta. So anyway, we get theta going to be 3 pi over 8. Okay, we can say theta is 3 pi over 8 plus some additional angles. Right, when n is 1, this is when n is 0. When n is 1, we get 7 pi. So let's do that. This is going to be plus that n pi. Okay? So n is 1, that's 4. We're going to get rid of this here. So here are my angles. Hold on. Let me double check that. We're going to say here, n is 1 now. No, I was right in the first place. I apologize. That's plus n pi. N is an integer. And this will be over 2. Yeah. There we are. Here's the general solution. Yeah, that's the general solution. I was correct. Sorry about that. And this is the real general solution of what you're looking for, though, because the angle here is theta. It's not alpha. Okay, here's your general solution down here. Okay. And the general solution, we're going to really have to go back and think. This is the location where we have horizontal tangents. However, there's a little bit more. What is this curve? Yeah. So we're going to have 2 locations on that circle, right? So remember the circle. I'm going to go back to that picture maybe. When your n value is 0, theta is 3 pi over 8. When n is 1, you say, what's my theta? It's 3 pi over 8 plus pi over 2. And remember what that does. Multiply the bottom by 4 and the top by 4. So your next value for theta will be 4 plus 3. Looks like it's 7 pi over 8. So here's going to be 2 solutions that we look at for horizontal tangents, okay? So 3 pi over 8, 7 pi over 8. So if I go back to the picture again, we got a couple of solutions for those horizontal tangents. And here's the device. More screenshot. Okay. Right up over here. I think we're using purple. This location, this location. Remember, this is the angle theta here. There's another theta. Okay, so theta is 3 pi over 8. Here theta is 7 pi over 8. Remember, this is the location for theta in which we have the horizontal tangents. That's what we just found. And if you said, what are the points? What's the location? Okay, we're going to give r theta. Remember, r was cosine theta plus sine theta. So we're going to leave this here in polar form. This is where we have the horizontal tangents. I'm not going to draw that line again with the ruler, but that's what we just found. So you guys remember, this is the location. So if you wanted to give the final answer in terms of a polar representation, all you'd have to do is remember, what's the definition of a point? It is r theta. So here are the two solutions. It is cosine, 3 pi over 8 plus sine 3 pi over 8. The angle was 3 pi over 8. And the other answer is cosine 7 pi over 8 plus sine of 7 pi over 8, and then that's 7 pi over 8 here for you guys. Horizontal tangents. All right, those are some horizontal tangents for you. And then similarly, vertical tangents, right? So now we got to do the vertical tangents. Let's go back and take a look. Yeah, we'll do vertical tangents as well now. So if you go back and you say, well, when do you have your vertical tangents here? Well, that's going to be when let's go back. That's going to be when our dx d theta is 0, right? Let's check our notes. Here we go, vertical tangents. Dx d theta is 0. So I want you guys to look at this, and this is going to change. Dx d theta, which is derivative of r cosine theta. So this dx d theta is the derivative of r cosine theta, and don't forget the value of r. R is right here. R is cosine theta plus that sine theta. So cosine theta plus sine theta times cosine theta. So for the vertical tangents here, dx d theta, which is d theta, r cosine theta, plug in the r value. Right, this is going to be cosine squared theta plus cosine theta sine theta. Again, because r here is replaced with cosine theta plus sine theta, and you distribute it. You're going to use the same identity here. Cosine theta sine theta, right? Cosine theta sine theta, way back up here. Should be somewhere. Yeah, cosine theta sine. We don't want a shade of blue. It's going to be 1/2 sine 2 theta. So we go, okay, 1/2 sine 2 theta, I guess. All right, let's use chain rule. 2 cosine theta, derivative of cosine is minus sine, plus 1/2, derivative of sine is cosine 2 theta, times 2, minus 2 cosine theta sine theta, okay, plus cosine of 2 theta. Now you said, what was cosine theta sine theta? Cosine theta sine theta that we see here, we know is going to be 1/2 sine 2 theta. We plug that in. This is 1/2 sine 2 theta. So all together here, we're going to get this equation here. negative sine 2 theta plus cosine 2 theta. Now don't forget, this derivative has to equal 0. So this was dx d theta equal to 0 means minus sine 2 theta plus that cosine 2 theta will be 0. You're going to get tangent 2 theta is 1 again. That trig equation, if I add sine 2 theta to both sides, you guys know how to solve this trig equation, right? This is adding sine 2 theta to both sides. You get essentially get cosine 2 theta equals sine 2 theta. Divide both sides now by cosine 2 theta. You end up with the equation tangent 2 theta equals 1. And again, this happens for, you can say, 2 theta quadrant 1, pi over 4, and quadrant 3, 1, 2, 3. So 1, 2, 3, 4, 5 pi over 4. Or we're going to say, I'll do it this way for you guys, pi over 8, 5 pi over 8. These are the angles. So you're solving that trig equation. And again, if you want to give your answer in terms of r theta, or I should say your answers, well, you have to remember what r was. R was the equation. R was cosine theta plus sine theta. That was what was given originally. Right? That's our r. Way back up here. I know that we were talking a lot about this curve. R is cosine theta plus sine theta. So we could leave this answer when because they say a point, they want a location. We're going to leave this here in terms of polar representation. So I just want to write down what color do we do that? Purple? Yeah, all right, whatever. Purple, who cares? So here's our purple color. R cosine, pi over 8. Plus sine pi over 8, and the angle was pi over 8. Here's the location. Cosine 5 pi over 8 plus sine 5 pi over 8, and the angle is 5 pi over 8, because we're leaving this answer when they talk about points in terms of polar. And there you guys go. Here's some calculus here. Anyway, just looking over some of these here, I'm thinking, ladies and gentlemen, yeah, let's try to do some arc length questions here. Okay, let's get you some arc length questions. So we're going to do some arc length questions now, but I'm going to change. We're going to do it in another video.